This video is lesson 3.6, solving proportions and using cross products. You should be on page 168. The term cross products represents the product of the numerator of one ratio and the denominator of the other ratio. You might be thinking, what in the heck did you just say? Okay, the wording is a lot more complicated than what it is. Cross product means the following. I'm going to draw it up here on the screen. Cross product means you taking, for example, in this proportion, taking 3 times 8 and then taking 4 times 6. Those are cross products. That's what this wording is saying. Now that gets us to what's called the cross product property, which is what I highlighted here. And the words for the cross product property are as follows. Cross products of a proportion are equal. So when you have a proportion that's true, if you take the cross products and multiply, you ought to get equal amounts. Here would be an example in the book. The fraction 3/4 is equal to 6/8. If you put it in your calculator, if you take 3/4, you'll get 0.75. Maybe I should write that down off to the side. And if you take the fraction 6/8 and put it in your calculator, 6 divided by 8, you get 0.75 again. So these are two equal fractions. Do you notice if you multiply the cross products, 3 times 8 is 24, 4 times 6 is 24. The cross products of a proportion are always equal. I'm just going to double underline this. They're always equal if the proportion is a true proportion. The proportion above here can be written in a couple different forms. It can be written in fractional form like you see here. It can also be written with colons, 3:4 equals 6:8. This is saying the exact same thing as this. It's just written in a different form. Now 4 and 6, those numbers are called the means. And I highlighted them in yellow. Maybe I should highlight them one more time in yellow in the picture above. Here are the means, 4 and 6. 3 and 8 are called the extremes. I'll highlight them up here again. 3 and 8 are the extremes. This is why the cross product property is also called the means extremes property. In other words, if you multiply the means and you multiply the extremes in a proportion, those should always be equal. Now we can use this fact to solve proportions, and rather easily. In fact, I would say the means extremes property, I'm going to write it up here, the means extremes property is the easiest property to use when solving a proportion. The means extremes property is the easiest way to solve a proportion, and as a teacher, I would highly recommend you use this method over what the book showed in 3.5. It's not that what the book showed in 3.5 was wrong. This just works no matter what the situation. Here are 3 problems that offer, well, 2 of the 3 for sure offer a great example of why this is the easiest property to use. Let's just do number 1 as a practice. 4 over A equals 24 over 30. Let's use the means extremes property to solve this. So I'm going to take the means, which are A times 24. I'll write it down as 24A. And that should equal the extremes, which is 4 times 30. So 24A should equal 4 times 30 is 120. And when I divide by 24 on each side, I ought to be getting that A is 5. I just used the means extremes property to solve this proportion. Now, that proportion isn't very difficult, but look at the second example. Here's a perfect reason why you want to know this property and be able to execute this property. Let's do this problem down here, and let's use means extremes to solve it. 3 over x equals 2 over x minus 6. Okay, so let's multiply the means together. That's 2 times x. Here are the extremes. I got to take 3 and multiply it by x minus 6. Now remember, we should simplify before we do anything else. I got to distribute to do that. So 2x would equal 3x minus 18, right? 3 times x and 3 times 6. All right, I got to solve this. Well, wait a minute. I got variables on each side. I can't have that. Let's remember, if we're adding 3x, we should take away 3x from each side. I want to get all my variables on one side. I want my constant on the other. So here's my constant all alone on the other side. And I can divide by negative 1. I'm getting 18. And then I can check it. Let's check. If I do 3 divided by 18, if I put an 18 in for x, 3 over 18 is 1/6. Let's go over here. If I put an 18 in for x, I'd have 2 over 18 minus 6 is 12, and 2 over 12 also equals 1/6. So I am getting this to work. If I plug an 18 in for x on each side, 18 must be the answer. Okay? Let's do one more. Let's go to this number 3. I'll work it off to the side here. So let's take the means and multiply. That's 5 times m minus 6. And that should equal 4 times m, which is the extremes. And when I distribute, I'd have 5m minus 30 equals 4m. Okay, I want to get all my variables on one side. I want to get rid of plus 5m. I'll take it away from each side. And when I do that, I get negative 30 on the left. I get negative 1m on the right. And I divide by negative 1 on each side to get m by itself. I'm getting positive 30. Let's check that. 30 divided by 5 is 6. Let's go over here. 30 minus 6 is 24. 24 divided by 4 is 6. This checks out. 30 has to be the answer. The means extremes property, let me just, again, I'm going to make a little check mark next in red here. This is a property you need to know and be able to execute. Let's talk about a scale drawing. A scale drawing is a two-dimensional drawing of an object in which the dimensions of the drawing are in proportion to the dimensions of the object. Okay? That sounds a little bit more complex than it really is. A scale drawing, here's some examples. It'd be like a map or a blueprint. It's a two-dimensional drawing where the drawing is in proportion to the actual size of the object. So in other words, it's going to look the same, it's just going to be smaller or bigger. Okay? A scale model is a three-dimensional model. Now you notice that's the difference. We had 2 dimensions versus 3 in the definition. Two-dimensional means like a sheet of paper, a drawing. A scale model is a three-dimensional model of an object in which the dimensions of the model are in proportion to the dimensions of the object. Here would be some examples of a scale model, like a model plane, or a model train, or maybe even a dollhouse that's to scale. When you have a scale drawing or model, there will be a scale that relates the drawing or model's dimensions to the actual dimensions. If you look on the picture above, you can see a scale. They're saying if you measure an inch on this drawing, that would be the equivalent of 12 feet in real life. So if I measured this bedroom and it happened to be 2 inches, or let's say it's 1.5 inches long. I don't have a ruler on me right now. Let's pretend that this is 1.5 inches long. This would be 12 feet times 1.5 inches, and that would tell me that this bedroom then would be 18 feet long if it is 1.5 inches. I don't know that that's the case. Okay, I'd have to actually measure it in my book. All right? But that would be an example of how I could use this scale to figure out the lengths of any of these rooms or the garage in this picture. We would use scales to figure out distances, for example, on a map. Like here they say Use a metric ruler and a map of Ohio to estimate the distance between Cleveland and Cincinnati. So if you take your book right now and your ruler, if you measure from Cincinnati to Cleveland, you're going to see it's about 4.2 centimeters. Now look at the scale. According to the scale, 1 centimeter is about 85 kilometers. So if I want to figure out how far is it from Cincinnati to Cleveland, I would write my scale 1 centimeter over 85 kilometers. There's my scale. That should equal 4.2 centimeters over unknown amount of kilometers. Remember, I said there should be some rhythm to this. Centimeters compared to kilometers equals centimeters compared to kilometers. There is a rhythm to that. Now, once you set it up, you can forget about the units. Let's just forget about them for a minute. And you can solve this. So let's multiply the means together. 85 times 4.2 should equal 1 times x. Well, all I got to do is take 85 times 4.2, that's 357, and that should equal x. And then I can check it. 4.2 divided by 357 should give me the same thing as 1 over 85, and it does. Now, I erased my units out. Let me put them back in real quick. Centimeters, kilometers, centimeters, kilometers. Does it make sense that my answer is in kilometers then? Okay. I'm going to pause the video there. If you have questions, you can ask in class.